Hi, Lee. Thanks so much for joining me today. I appreciate it.
It's great to be here. Thanks for the invitation.
Absolutely. So, a little bit of a background. I met you at the ASMS conference this past year where you were giving some presentations, and I just really loved how you were able to explain some very complex topics in an easy to understand way. I was hoping you could talk about some of the misconceptions that students have about mass spec when they first start learning about it.
Sure. I think the biggest misconception people have is that I'm not going to be able to understand this. You walk into a class, you're like, okay, mass spectrometry or chromatography, mass spectrometry. It's a very complex topic, and maybe I'll learn a couple of tricks here and there, but I'll never be able to understand it. I think that's the biggest hurdle that I have in telling people. The first thing I say is just suspend all your disbelief that you're not going to understand this. And what I explain it as complicated things like chromatography, mass spectrometry, it's really just a bunch of simple things stuck together, and when you put them all together, they look complicated. So let's take the simple things one step at a time. So I think the biggest hurdle is people sort of have a mental block that they're not going to understand this.
I was amazed when I read how many professional scientists you've trained at Axion Labs. Could you tell us about Axion?
Sure. I started Axion about 25 or 30 years ago, and Axion is a real chromatography laboratory. I'm standing here, a bunch of LCs and GCs, but we're mainly a training facility. Scientists come to us for 5 days, they hang out in our lab, they learn chromatography, they take the instruments apart, put them back together, and they walk away feeling very comfortable with chromatography. So that's essentially what we have become, this training facility. So we've done about 14,000 scientists over the years. We've also done about 650 lawyers, which is really funny. Imagine lawyers coming into a hardcore science class. So everyone's invited. I always say the only requirement for my class is that you want to learn chromatography. Even though you might consider this to be like a postdoctoral kind of a class, it's more your interest in chromatography and not your background.
What drew you to teaching chromatography and mass spec?
You know, I was very fortunate to, I went to graduate school to work for this guy named Harold McNair, and Harold McNair was one of the grandfathers of modern chromatography. So, in working for Professor McNair, his job was to get the word out there, to explain to the world how chromatography worked, and he really sort of taught all of us that our job in life is to do chromatography and sort of go out and preach the word of chromatography. And so I got bitten by the bug early on. I think it's neat because there's literally more than 1 million GCs in the world right now, let alone another million HPLCs. So there's 2 million chromatographs in the world right now, which means 2 million people are standing in front of them, but most of them have no idea why they're pushing buttons on the front of the instrument. To me, it's a wonderful challenge to say there's literally millions of people out there who are doing chromatography who do not understand how it works. So what a great opportunity to go out and teach them. I got, like I said, bitten by the bug in graduate school. I went working on my PhD under Harold McNair, and I guess that was 30 years ago, and I'm still at it.
That's great to hear. Well, I'm really excited for my audience of academic researchers and people who are just learning chromatography and mass spec as undergraduates. Really excited to bring your lesson to them today and excited to learn from you.
I'm, like I said, always happy to share my knowledge freely wherever I can. So I'm excited as well to share this.
Yeah, let's get into it.
Okay, so what I'd like to do is use some slides to help you understand chromatography mass spectrometry. As complex as a topic as this is, suspend your disbelief, because as we go through it, I think at each point you're going to say, hey, I think I understand that. And we're going to go on to the next part. So let's talk about gas chromatography mass spectrometry. And like I said, suspend that disbelief that you're not going to understand it, because what I like to look at is the ways to teach chromatography is by using analogies, what are called transferable concepts. I use a lot of car analogies because you understand how a car works. So let's translate that over to chromatography. So GC mass spec is this great topic, and to me it starts out with the GC part of it. Now, when I talk about mass spectrometry, the mass spec's going to be the same for GC mass spec, LC mass spec, but the front end is going to be a chromatograph. It's going to be either a GC or an LC. And the first question is, why do we have a chromatograph as a front end? And the reason is mass spectrometry. Mass specs are really good at identifying unknowns. They give us enough data to identify a total unknown, but unfortunately, a mass spec does not work well for mixtures. And in real life, just about everything you're going to see is a mixture. Rarely do you run into the problem where your boss comes to you and says, I've got this stuff that's 99.999% pure, but I don't know what it is. That's not very common. Hey, I found this greasy, gooey stuff dripping out the back of the plant. I want to know what's in it. It's a mixture. Put a mixture into a mass spec, you get worthless information. But what is a GC? A GC is the world's best separation tool. And what does it do? It takes complex samples and separates them into pure compounds. Once we separate by GC, we can then identify by mass spec. Because remember, mass spec works great for pure compounds. A GC creates pure compounds out of mixtures. So gas chromatography, great separation tool. When we combine mass spec and GC, we get the separating power of GC and we get the identification power of mass spectrometry. They're inherently very compatible. They work about the same mass range from 2 to about 1,000 molecular weight. So they cover a fairly similar range of analytes and compounds. So GC and mass spectrometry are inherently compatible. When we talk about LC mass spec, the challenge there is just the interface. Mass spec is easy, LC is easy, but the interface in LC mass spec is the challenge. GC mass spec, no challenge there. It's pretty simple for us to connect a GC to a mass spec. In fact, if you look at a modern GC mass spec, here's a picture of the Shimatsu, you'll see that the mass spec is really just that little circle part. It's a small part of the whole instrument. It's the most expensive part. So how do we get the mass spec connected to the GC? Well, it's simple. We have just this interface. It's really just a heated transfer line. We have a column. We just take the end of our GC column. We literally stick it into the source of the mass spec. There's no interface really. It's just a heated transfer line that allows us to stick the column in the mass spec. So don't worry about band broadening and that kind of stuff that we worry about when we're doing LC mass spec. So we asked the big question, and that is, how does mass spectrometry work? So mass spec, again, this is sort of, it's not even high-end chemistry. This is high-energy physics. So one of the ways I explain mass spectrometry is to sort of say, pretend like this is a science fiction story. I'm going to tell you this great story. It's science fiction. It's really fascinating. And at the end of the story, I'm going to say, actually, everything I just told you is true. So let's start off with understanding how a mass spec works. Before we do that, let me take a step back and explain and remind us how chromatography works. Because chromatography is the way we're going to get into the mass spec. So chromatography is a separation tool. We have a typical GC, like one right here behind me, and we'll have what's called a capillary column. And what it is it's a long length of glass tubing. It's a tiny little hole. It's a 0.25 millimeter inner diameter. And on the inside walls, there's a thin coating of a stationary phase, like a thick viscous liquid. So what we're going to do is we're going to take your sample, vaporize it, blow it through the column. And as it blows through the column, each analyte, each chemical in your sample is going to interact with the stationary phase. The more that it likes the stationary phase, the more time it spends on the column. So GC separation is based on the relative affinity for molecules on the stationary phase. If they like the stationary phase, they hang out a long time. If they don't like it, they run through very quickly. So the analogy I have for chromatography is it's like me going to a shopping mall with my sister. So I walk into this mall. It's a very long linear mall, and there's a moving sidewalk in the middle. And you stand on the moving sidewalk, and it transports you through the mall. If you see a store that you like, you get off the sidewalk, spend time in the store. So the first store we come up to is a dress store. So my sister and I enter the mall at the same time. We're going through this mall at the same time, but she gets off the moving sidewalk to spend time at the store. I keep moving, so by the time she comes out, I'm now 100 feet behind her. Then we cruise through the mall. We get to another store that's accessory shop, hats and gloves and purses. She goes and spends time. I keep moving. I'm now 200 feet in front of her. We then get to the final store, which is a shoe store. She goes and spends time. We call this irreversible adsorption because she goes in and never seems to come out. So at the end of the mall, who's going to come off first? Who's going to be standing there looking at their watch waiting? Well, I'm going to come off first because I have very little interest or very little affinity for the stores inside the mall. The same thing happens in chromatography. Every single molecule enters the column at the exact same time, but as they travel through the column, some have a higher affinity for the stationary phase than others. Those molecules lag behind, and that's the basis of separation. So if you could understand that shop mall analogy, you could totally understand GC. A bunch of molecules entering the column at the same time, they interact with the stationary phase. The more they like it, the more they lag behind, and that gives us our retention time, the amount of time it takes a molecule to travel through the column. So now think of what that means. Not only can we use that to identify things, but we have now truly separated our complex mixture into pure compounds. Now that we have a pure compound, we can send that into the mass spec to be identified. So now let's open up this big package and ask, how does a mass spec identify things? Well, a mass spec is going to weigh the molecule. And if we weigh the molecule, we get its molecular weight. So instead of saying, hey, I got a peak that comes off the same retention time as benzene, I can say, I have a peak coming off retention time of benzene, and that molecule has a molecular weight of 78, just like benzene. Wouldn't that be pretty cool? So that's what mass spec gives us. It gives us the molecular weight and then some, and we'll explain that in just a bit. But the first question, how does a mass spec weigh a molecule? Because you know that we cannot directly weigh a molecule. We are light years away from that technology. You know, the best balance you could buy, I mean, I've got a 5-place balance, the Analytical, I got a 6-place balance back there. You could buy a 7-place balance, which I think is just about the biggest one you can get. To weigh a molecule, we would need a 23-place balance. So nowhere near the ability to weigh a molecule directly, but we could weigh it indirectly. And that's what I'm going to show you here. So in the mass spec, the first thing we're going to do is we're going to ionize. We're going to put a charge on your molecule, and we're going to use that to weigh the molecule. So bear with me here, and what I'm going to do is I'm going to draw up here for you I'll start with saying an overly simplified mass spec. So I'm going to describe a real mass spec, how it works, and then I'll add some layers to get us to the modern quadrupole mass spec. So this is the end of my GC column. And I've got these showing here, 3 little green molecules coming off the GC. So separation has already occurred, beautiful separation. These are 3 molecules of the same compound, and they are now entering the mass spec. So in order to weigh them, the first thing I'm going to do is I'm going to put on a charge. To do that, I use what I call an electron gun. It's really just a filament, but imagine an electron gun, and I'm shooting high energy electrons at your molecule. 70 electron volts. This electron is so powerful, it could go in and ionize your molecule. It could even smash it apart. So what's going to happen is I'm going to shoot these electrons at your neutral molecule, and if I hit your molecule, it will become positively charged. And I got to tell you, that's the first thing that confused me about mass spectrometry, because I know a little bit about electrons. Electrons are negative, right? So if I hit something with a negative electron, shouldn't it become negative? The answer is nope, it becomes positive. Well, why is that? Well, you know that a molecule is mostly empty space. 99.9% of a molecule is totally empty. The only solid part is the nucleus of the atoms, but the majority of the molecule is just these electrons whizzing around your molecule, your nucleus. So what we have is a sphere of electrons. So the sphere of electrons is your molecule. We have this high energy electron that comes into your sphere. Your own electron says, "Ooh, I'm afraid of that. I'm repelled because we're both negative." It gets kicked out, and you are left with one fewer electron, which means you now have a +1 charge. So in GC spec, if a molecule becomes ionized, it always takes on a +1 charge. We don't get multiple charges. In LC spec, we get multiple charges. In fact, we do that on purpose in order to, if you want to weigh a protein, that weighs 100,000 molecular weight, no way it's going to happen unless we could put a lot of charges on that protein. So that's in LC mass spec. In GC mass spec, if it gets ionized, it's a +1 charge. And here's the reason. As soon as it takes on a charge, it's sitting next to what's called the repeller electrode, which is a positive voltage. So as soon as something has a positive charge, it immediately gets kicked out of the source. So imagine this molecule is now positively charged. It gets kicked out of the source, which means it has forward momentum. The molecule is moving from one end of the mass spec to the other. On the other end of the mass spec, we have the detector. Now I'm drawing it as a target. So my goal is here, I'm shooting the ionized, the charged molecule. I'm shooting it out of the source, and I'm going to try and hit the detector. I'm going to try and hit that target. But when I shoot this towards the target, it's going to have some trajectory. And that trajectory is going to pull my molecule down, and it's going to miss the target. So imagine I have a molecule that weighs 100 molecular weight, and I shoot it out of the cannon. And let's imagine that gravity is pulling down on that molecule that weighs 100. So it's pulling down with a force of 100. Well, what if I could put in an electrode or a magnet, and I could put a positive charge or a north pole on it, and I could set it to push up with a force of 100. So gravity is pulling down with a force of 100. I'm telling this electrode push up with a force of 100. So if this molecule weighs exactly 100, it'll go all the way through and it'll hit the target. So at that moment in time, the target's been hit. He knows it's been hit. He has no idea what hit him. So the target asks the electrode, "What voltage are you set at right now?" And this electrode says, "Oh, I'm set for 100 molecular weight." So now the target realizes, the detector knows that it just got hit by something that weighs 100 molecular weight. Now, if something weighs 101, gravity's pulling it down too much, it's going to miss the target on the low end. If something weighs 99, it's going to miss the target because the electrode is pushing up too much. So the only molecule that can hit the target at right now must weigh exactly 100 molecular weight. Then I change the electrode to 101, 102, 103, 104, and I scan all day long from 0 to 1,000. And it's scanning so fast that it appears that all the masses show up at the same time. We're really measuring them 1 to 1,000, 1 to 1,000. The reason is the scan rate. On some of the newest mass specs out there, they go up to 40,000 AMU per second, which means I can scan from 0 to 1,000 40 times every second. So by doing that, we can tell exactly what something weighs based on what voltage the electrode is set at for that molecule. Now, does that make sense? And to me, the funny thing is, hopefully, it makes sense a little bit. And I keep talking about the electrode or a magnet. You know, electricity and magnetism are two sides of the same coin, right? If you have a flow of electrons in a wire, so if you've got electricity going through a wire, you, by definition, have a magnetic field around it, and vice versa. We can induce electricity. So what I just described for you is called a magnetic sector mass spec. Now, you're probably never going to see one of those. 10 years ago, this was the $1 million mass spec. It would take the entire room, two-ton magnets. But I like to start with that because it's somewhat understandable. You've played with magnets before. You can do magnetic levitation, right? You can make one magnet sort of float above the other just based on magnetism and gravity. So for proof of that, I have this cool little thing sitting on my GC. If any of you are wondering, what that cool thing sitting on the back of the GC? Well, this is it's actually, this is the globe. So this is the Earth, and it has a certain weight. It's pretty heavy, and the top of this is a magnet. So if I stick it up there, it just sticks to the magnet. So the magnet is so strong, it's holding up. The gravity is not strong enough to pull it down from the magnet. But if I put just the right gap in here, and I'll see if I can do this live, just the right gap, then what we're looking at there is magnetic levitation. There's no wires here. I feel like I'm a magician, right? There's no wires holding it up, and with a little bit of luck, you can actually spin it. So that's magnetic levitation, which means the magnetic power is the exact same as the weight of that globe when it's that exact distance. So it works. We know it works. So this is the first way I describe mass spectrometry is by talking about magnetic sector. So hopefully that makes a little bit of sense, right? So now let's add another layer. And now we're going to get to a quadrupole. So first, remember, this guy is going to weigh the molecule. It's going to make a little tally. It's going to say, I just got hit by something that weighs 100. But modern mass specs, or most of the mass specs that you're going to see out there, are based on what are called quadrupole, which means instead of one electrode or one pole, I have 4 poles, hence the term quadrupole. And in this case, I have one below, one above, one in front, one behind. And if we were to turn these 4 rods on their side and just look down the rods, it would look like this. So we're looking down those rods, and these rods are maybe about the size of a pencil, and we're putting a voltage and we're pulsing it on those 4 rods. So what happens is, let's say I'm 100 molecular weight. I just got kicked out of the cannon. I have my positive charge. I have forward momentum, and then I enter this quadrupole. So above me, I have the pole above, below, and to the right and to the left. The one above me turns on, and I'm attracted to it. So I have forward momentum already, but now I have upward momentum. And then the right rod turns on. So I start moving right, bottom, left, top, right, bottom, left, top, right. And if I have just the right molecular weight, I will have a stable corkscrew trajectory, and I'll make it all the way through the quadrupole. Boom, I'll hit the mass spec. So what if I'm off weight? Instead of 100, what if I weigh 99? Well, 99 is going to have an elliptical trajectory, and eventually, boom, it slams into a rod. What about something that weighs 101? It is not stable enough, and it slams into a rod. So the only mass that's stable enough to get from one end of the mass spec to the other must weigh exactly 100. Then I change the voltage to 101, 102, 103, 104, and I'm scanning 0 to 1,000 really, really fast all day long. And that is how modern quadrupole works. It's really a mass filter. And it basically says no one can get through this mass spec right now unless you weigh exactly 100. And then the door closes. And then the next one opens, 101, 102, 103. And you can imagine this door opening and closing really, really fast. And then all of a sudden, a molecule makes it through and hits the detector. And the detector says, what gate was just open? And this guy says, oh, gate number 178. So that molecule must weigh 178. Does that make sense? So essentially, we're spinning molecules, and only a certain molecular weight will be stable at any given time, and only that molecular weight will make it all the way through. I said to think about this as science fiction, didn't I? Well, yeah. Okay, so believe it or not, that's what really happens. The molecules are spinning, and if they have the right molecular weight, They'll spin in control throughout the entire quadrupole. If they're slightly off weight, then they will just spin out of control and we'll never see them at the detector. And that is how a modern quadrupole mass spectrometer works. So 4 poles, and on those 4 poles, we're placing a voltage. We actually place a radio frequency. That's where it gets a little confusing. But radio frequency is just electricity and magnetism in the 2 dimensions. So anyways, we create this energetic field, and only one molecule, only one mass at a time is stable. So I just described how we can take a molecule and weigh it, and that is pretty impressive. But that's not the most impressive part, because the weight of a molecule all by itself is not that useful. I mean, there are a lot of isobaric compounds out there. The bigger a molecule is, the more molecules that are out there that could weigh that amount. So let me give you a crazy analogy. And let's say I'm the witness to a bank robbery, and I'm there. The police interview me, and they ask me to describe the bank robber. And I say, okay, I'm gonna be very careful on this. The bank robber was a human being. It was not a dog, not a cat, was not a raccoon. The bank robber was a human being. The police would say, "You've been no help at all. You've done nothing to advance this case." Well, that analogy, that's a GC with an FID, flame ionization detector, the most popular detector in the GC world. FID sees something. Yes, I saw it. Hey, FID, what did you just see? I saw a molecule that contains organic carbon. Wait a minute. 70 million different compounds contain organic carbon. So FID by itself is not terribly useful. But let's say I'm a witness to the bank robbery, and I tell the police, yes, the bank robber was a human being. We've established that, not a dog or a cat. And I know that human being weighs exactly 172 pounds, exactly 172 pounds. The police would say, well, you've certainly eliminated a lot of people from, let's say, the city of Chicago. I live here in Chicago. But let's face it, there's going to be over 1,000 people who weigh exactly 172. So I would rather have the person's name, address, phone number, and current location. Well, that's what this next step brings us. In chromatography and mass spec, we call this fragmentation. Fragmentation is going to give us the level of detail where it must have been this molecule to the exclusion of all other molecules in the world. No other compound could have given me this data. So now let's talk about fragmentation. So you understand how we weigh a molecule. So when I have a molecule coming off a GC, it's not, when the peak comes off, it's not one molecule or 2 molecules. It's like 2 billion molecules. And of those 2 billion, some of them ionize, simply take on a charge and move on through. And some of them get smashed apart. We hit it with this high energy, and such high energy that the molecule breaks in half, or a piece breaks off of it. And then those 2 parts are now ionized, and we will see those as they travel through the mass spec. So you can imagine that not only are we going to see the molecular weight, but we're also going to see all the parts that fell off the molecule. So my analogy is, let's say there's someone on the rooftop of this building. I'm here at the lab downtown Chicago. We have a 7-story building. Let's say there's someone up on the rooftop, and they have a thing. We don't know what the thing is. We have to figure out what it is. They take this thing and they pack it full of dynamite and they blow it up. And we're watching out the window and we see parts fly by. So I see 4 car tires, 2 car doors, a car hood, and a steering wheel. What was it that they must have blown up? Sounds like a car. Could that have been a minivan? No, I didn't see those funny sliding things. I just saw 2 regular doors. Could that be a 4-door sedan? No way, because I didn't see 4 doors. I only saw 2. Could that be a Corvette? Yeah, sure, because it had 2 doors. So what I'm getting at is every single piece that I see fly by the window, if I'm calling that thing a Corvette, I better be able to place every single piece on it. And let me give you an explanation of why this is so important. When you start doing GC mass spec or LC mass spec, people will say, oh, don't worry about the chromatography anymore. Let the mass spec sort it out. I totally disagree with that statement, because I believe if you're doing GC mass spec or LC mass spec, the separation is even more important, because if you get 2 molecules that enter the mass spec at the same time, you get worthless information. You get masses from both molecules, and you can't identify either of them. So here's my example. We're watching out the window trying to figure out what they blew up. We see 4 car tires and the 2 car doors and the car hood, and a steering wheel, and an outboard motor. What was that? Well, I can't think of anything on this planet that has 4 wheels and an outboard motor. That was a car and a boat going through the mass spec at the same time. They go through at the same time, they get smashed apart. We see the masses from both molecules, and it makes no sense at all. If you want to tell me what just went through the mass spec was a boat, well, show me where the 4 tires go. If you're saying it's a car, show me where the outboard motor goes. So that's an example of when we do mass spectrometry, We smash the molecule apart. When we see the fragment, all the fragments must have come from that molecule, so we should be able to put it back together. Okay, so that is fragmentation. That gives us a fingerprint, a unique fingerprint to that molecule and that molecule alone. Things that are identical give identical mass spectra. But what we're going to do is we're going to see even structural isomers. We'll see differences in their mass spectra. So what I just described is running a mass spec in the scan mode. We put a sample in there, we smash it apart, and we scan to see what all the fragments are that have come off. So that's really cool. We make our little molecule spin, and that is how we're going to identify or weigh and fragment in order to identify the molecules. So this is what we get. The output is a mass spectrum is one, mass spectra is multiple. And this example, let's take a look at the ethylbenzene. Ethylbenzene, the highest mass is 106, and we call that the molecular ion. Molecular ion is the highest mass, and it's what the molecule weighed before it fell apart. So we're looking for a molecule that weighs 106, which is ethylbenzene, and then it loses something to create another fragment, and the most stable fragment is the most abundant fragment. In this case, it's 91. So 91 we call the base peak. Base peak is the tallest, and what we're looking at here is abundance. The most likely to happen is the abundance. So the most abundant we call the base peak. The base peak is important because every mass spec search routine is based on the base peak. So that's why it's important nomenclature. We could also look at this molecule and say, okay, what must have happened to go from a 106 to a 91? Something fell off. What fell off? Something weighs 15. What weighs 15? A methyl group. So if you look at ethylbenzene, that methyl group on the end is easy, it falls right off. And then it forms this 91 peak, this 91 mass called the tropylion ion, sort of like a toluene, but only CH2 on the top. That's a very stable ion, one of the most stable ions in all of mass spectrometry. The reason why it's so abundant is because it doesn't like to break apart. So imagine if you had a car and you blew up a car, I bet parts of it would not break. Maybe the axle, it's just a solid piece of steel. No matter what you do, it's never going to break. So that's the fragment that no matter what happens, that fragment is always there. That would be sort of like the base peak. Okay, so how likely is it for both methyls to fall off, like for the ethyl group to fall off? How likely is it to form a 78? Not very likely. So these are probabilities. Remember, we don't have one molecule in our peak, but like 1 billion. So of the 1 billion molecules, I don't know, I'm going to guess, 300 million of them became a 106, stayed together. Maybe 600 million of them became 91 because that was really stable. And then a few million became the other mass that we see here. So let's look at another example, naphthalene. In naphthalene, what's the molecular ion? Well, that's 128. What's the base peak? Yeah, 128. So based on what you know about mass spectrometry, how stable is the naphthalene molecule? It's really stable. How do we know that? Well, I just blasted it with the biggest gun that I have, with the biggest, highest energy electron I have, and I couldn't make it fall apart. It's so stable, it says, there's nothing here that's going to fall off. So this just shows why we get the fragmentations we have. It has to do with the stability of those fragments. Everything I've talked about so far is mass spec in the scan mode. So scan, we're scanning all the masses. We use that to identify things. You get a total unknown, you have no idea what it is. We do a scan, we search the library, it tells us exactly what it is. When you're doing scans, the output is called the TIC, the total ion chromatogram. So it means it's a chromatogram that if a mass showed up at any mass, if fragments showed up at any mass, we're going to count it as part of the peak. So we always start with the TIC. It's like the universal chromatogram of our sample. And then behind each peak is an entire mass spectrum. And that's going to be the fingerprint. Okay, so there's another mode that we could use with a single quad, and that's called SIM, Selected Ion Monitoring. In this case, the example would be, I know exactly what I'm looking for, but I want to find it at really low levels. So to do that, we're not going to scan all 1,000 masses. We're just going to sit on 1 or 2 or 3 masses. So think about, let's say I could scan 1,000 masses in a second. We can scan faster than that, but so that means I can spend 1 millisecond on each mass. 1 millisecond on mass 1, mass 2, mass 3. So if I could spend 2 milliseconds on my mass of interest, then I'm going to get better sensitivity because signal to noise ratio, the noise starts to cancel itself out. If I could spend 3 milliseconds, I get even better sensitivity. So of the 1,000 milliseconds, if I spend 333 milliseconds on my ion of interest and then maybe choose 2 other ions of interest, then I can get, we're talking 30-fold, 100-fold better sensitivity. So in my world, let's say we do a lot of work with all kinds of different industries. The forensic folks, you have 2 different parts of the forensic world. Solid draw, sort of the DEA. What do? I got a bag of white powder. is there cocaine in there? We do that by scan because I want to have the whole fingerprint. The other world of forensics is drugs in blood, drugs in urine, drugs in the hair follicle. So if I'm looking for cocaine in a hair follicle, I need a lot of sensitivity. In that case, I'm going to say, don't scan from 0 to 1,000 all day long. Just sit at mass 303, molecular weight of cocaine. Just sit there all day long, and then we'll be able to find it at extreme low levels in blood and urine. So SIM allows us to look at just the molecule, just a mass of interest. Unfortunately, with SIM, we lose a lot of the identifying power. We don't get the whole fingerprint anymore. We just get 1, 2, or 3 spots of the fingerprint. So in general, we're going to run tick to identify things, and the tick is to identify things, and then we're going to run sim in order to get really, really good sensitivity, especially in a complex matrix. So here's an example of a single quad. So a single quad produces what are called searchable spectra. So in this case, we ionize the molecules, they make it all the way through. And the example I'm showing you here is a pesticide. It's called DDE. So we're analyzing our grapes or our apple juice for this pesticide, and we want to make sure it's not present. So this is the mass spectrum of this DDE, of this unknown. It has a mass at 318. It's got another mass at 246. Notice it has like a cluster of masses. This is because this is a halogenated compound. Chlorinated compounds always have what I call doublets, because there's two different, very stable isotopes of chlorine. They're apart by 2, so you'll always see these doublets of peaks masses that are apart by 2. So we run this total unknown, and on top the unknown spectrum. So it's a sample of apple juice, and I run it. I find this peak. I smash apart the peak, and I get this spectrum. And I say, I wonder what this is. I tell the computer, hey, computer library, search through this, see if you've ever seen this before. The libraries are, I have an older library. We have 220,000 compounds in it. So the newer library is even more than that. Basically, any compound you'll ever find on this planet, it's pretty much in the library. Unless it's a really brand new molecule, it's going to be in the library. So in this case, the NIST library comes back and says, yep, I found a good match. This is the same spectrum as para DDE. And what's it doing? It's comparing the two. It's saying, okay, I see a 318. I see a 316 as well. I see the 246. I see the 281s. I see 176. So it's looking at the pattern and saying, yep, I see a really good match between your unknown and this NIST library match, which is DDE. So at this point, I can conclude that it looks like there's pesticide in the sample. Okay, so that's how we do it if we're doing scan. But scan works great if you have a relatively clean sample. What if we were to run sim? So in this example, we're going to monitor 8 ions instead of all 1,000 or 486, 465 in this case. So typically, I would say in real life, in the forensic world, we typically choose 3 ions. The first one we call the quant ion. The other 2 we call qualifier ions. So we'll measure the 3, and we usually quant on the quant ion, and then we say just make sure the other 2 ions are present in about the right ratio. That helps in the identification. In this case, we're monitoring 8. It's a little overkill, but you get the idea that we're not seeing anything except for the 8 masses that I asked for. So 318, 316, 277, 263, 246, 248, and 79. And we'll see nothing else but those. So why is that cool? Why would that be important? Well, let's say I'm trying to find a pesticide in a complex matrix. In this case, this is spinach. Ooh, I knew spinach was bad for you. Okay, so this is spiked. This is pesticide spiked into spinach. But look at the peak. So if you look at the top chromatogram, that's the tick. That's a scan, right? We'll run a scan. That's the tick. There's pesticide in there. Can you see the peak? It's teeny tiny. It's right there around 24 minutes. It's teeny tiny. We can barely see it. But if I tell the system to run in the sim mode, and I say, okay, just look at 246. Don't look at any mass but 246. Notice what we see. We see one giant peak for the pesticide and essentially nothing else. That's why we like running in the sim mode, because it's like looking for a needle in the haystack, but we just get rid of the haystack and we see nothing but needles. Okay, so that's great if I'm trying to find a small amount of compound in the matrix of something. With a single quad, I could run sim. Now, the hottest thing going out there today is the multi-quad, the triple quads. So let me introduce you to this concept and just really explain why are triple quads out there? What do they bring to the table? Triple quads are not bringing anything to the table in terms of identification. We could search through the library. We could do that on a single quad. That's all you need to identify things. But what the triple quad brings to the table is the ability to find ultra low levels. So instead of a part per million or a part per billion, we're now talking about parts per trillion. In fact, there's an EPA method calling for parts per quadrillion. So how are we getting to these outrageously low detection limits? We're doing that with triple quad, either LC mass spec triple quad or GC mass spec triple quad. So in the general scheme of things, in GC, most GC mass specs are single quads. A benchtop GC mass spec is the most useful instrument in the world because we can identify any unknown. LC mass specs are almost always triple quads. LC single is not terribly useful. LC triple, very useful. In the GC world, GC single, very useful. GC triple, useful really only for ultra trace analysis. That's what it brings to the table. So let me explain how this works. First of all, how many mass specs are there? Are there two or are there three? We call it tandem mass spec, MSMS, triple quad. Really, there's only two mass specs. The third one, the middle one, it's just a collision cell. It's a tiny little collision cell. The first mass spec is we're going to smash molecules apart in the source. We're going to let the first mass spec sort of sort things out for us, and then we're going to use the second mass spec or the collision cell. We're going to smash that molecule apart. So whatever came off mass spec 1, we can smash it apart and then weigh it and see what came off, what the fragments are on mass spec 2. So let me give you some real examples. So again, this is back to that pesticide, is DDE. We know it has a molecular weight of 318. We know that we have an ion there at 246. So in this case, we're going to run this through mass spec number 1. We're going to smash it apart, and we could consider looking at only mass 246 and nothing else. But if we do that, we'll get our molecule of interest, but unfortunately, there's something else in the sample that's interfering that also has a mass of 246. Remember, it doesn't have to be the molecular weight of a molecule. It just has to be a fragment. So there's something in the sample, and you can see how part of the 246 is red versus green. Part of it is because of our molecule, and part. So what we're going to do is mass spec number 1, we smash it apart, and then we set mass spec 1 to sim 246. So only 246 makes it through. Nothing else makes it through. Then mass spec number 2, we're going to smash it apart, and we're going to see what comes off. So when we smash 246 apart, we see the 246, which is the molecular ion. We see a 175. We see a 105. Those came from our pesticide of interest. That other noise in there, those red peaks, those are masses that came from something co-eluting. So you get the idea. We know exactly what came from our molecule because we can take a DDE by itself. We sim the first one, 246. We smash it apart. We see exactly what comes off. And that's the 246, the 175, the 105. So now mass spec number 2, we're going to sim that. We're going to tell it, don't scan all day long. We know what we're looking for. We're going to sim it. In this case, we're going to sim on 175 and 105. So what does that mean? The only thing I will detect is a mass of, let's say, 175 that came from a mass of 246, that came from a 318, that came from a DDE peak. So what are the chances that there's some random molecule in this universe that happened to make it through all those, that came off the same time as DDE, that smashed apart, that had a mass of 246, it smashed apart, it had a mass of 175. The chance of that happening is 0. So GC mass spec triple quad, our signal to noise ratio goes outrageously high, and that gives us sensitivity. Now, by doing this, we really, this only works for targeted analysis. We only will see exactly what we look for. We'll not see anything else. So that if there's another pesticide right next to this, if we're not looking for that mass of a mass from that pesticide, we're never going to see it. So this is incredible for sensitivity, but we lose the ability to see what else is in the sample. We only go after the target. So in this case, when you do triple quad mass spec, this would be called the monitoring the 246-175 transition. So it means we smash it apart, we grab 246, we smash it apart, we grab 175. So we would call that the 246-175 transition. Okay, so a picture's worth 1,000 words. This is a great series of chromatograms. On the left side, we have SIM. We have a mass spec. We've told it only look at mass 246. That's very, very selective. We're going to see nothing in the sample unless things have a mass 246. So apple juice is easy. Cabbage has some other things in it, but they don't interfere with the peak. Ginseng, not such a problem. Orange juice, we have an issue. There's something in orange juice that's co-eluting with our compound of interest, and it has the same mass. Look at spinach. Spinach completely wipes out that portion of the chromatogram. So there's pesticide there, but it's completely masked by the other molecules in spinach that come off at the same time. Now, if we do a triple quad, it's called multiple reaction monitoring, MRM. We're doing the 246 to 175 transition. Look at apple juice, cabbage, orange, spinach, every single one exactly beautiful, clean peak. The reason we're looking for a fragment of a fragment, and even though there's a bunch of things coming off right on top of the pesticide peak in spinach, none of them have that same unique transition. So hopefully that explains why triple quads are out there. They're going to grow in use because everyone wants to see smaller amounts of materials, and triple quad's going to get us there. So everything I talked about mass spec wise is going to be the same for LC mass spec, the exact same thing when we talk about the multiple reaction monitoring, the triple quads. The biggest difference between LC mass spec and GC mass spec is in LC mass spec, we're going to ionize the molecule before we get into the mass spec. So it's called atmospheric pressure ionization, API. So in LC mass spec, we ionize first. If you're running acids and bases, then we can ionize them in solution just by changing the pH. So we create ions in the LC, and then we suck the ions into the mass spec, and the rest is the same. So that's like mass spec talk on the back of an envelope. And hopefully, what you take from that is mass spectrometry, incredibly popular and a useful tool. Most people have no idea how it works. Now you understand at least the fundamentals of the separation and how they apply to the whole world of identifying things. I think to me, one of the biggest things we always say is GC mass spec problems are GC problems. People always make a mistake on the GC parameters. It's pretty hard to make a mistake on the mass spec parameters because let's face it, there's nothing on the mass spec that you actually set yourself. There's no buttons on the front of the mass spec. If there are any, we never touch them. We auto tune the mass spec. So all mistakes that are made in GC mass spec are on the chromatography side. They inject too much, the separation is not good enough. So that's why a lot of what we do, we teach chromatography because that's the fundamentals that is required before you start doing the fancy detectors on the back end. Once you got the chromatography, the mass spec stuff is easy. So I'm happy to answer questions.
Absolutely. Yeah, it's always depressing to see that dirty dozen list of foods that have the highest level of pesticides. And I believe spinach is always on there, and I believe strawberries are typically in the number one spot.
Yep, those are part of that dirty dozen. And you'll find them if you, GC-MS spec is the way that you're going to get to the levels low enough to actually find those residual pesticides because the amount that's left over is really, really low. And that's the challenge is to get to those low levels.
I suppose this is more of a question on the teaching aspect, and I think you demonstrated it during your talk, but you've certainly trained a wide range of chemists, people who are, you mentioned the DEA, food science. How do you adapt the explanations for these different audiences?
The funny thing is what I've learned over the years is I use the exact same explanations, the exact same analogies if I'm teaching the Cub Scouts when they're coming through or I'm teaching the MD PhDs, because the reality is we all have these common experiences and like an automobile. It's really hard to understand how an automobile works. You have to have a PhD in physics because you have to understand adiabatic expansion of the engine, and torque transfer, and gear ratio. But we all know when we get behind the wheel of a car, you push the pedal on the right and the car goes faster. The pedal on the left, the car goes slower. So here we have this incredibly complicated device, and you operate it every single day. So don't be afraid to operate one of these. So I like using the same analogies because a lot of people say, are you dumbing it down? Do the scientists sort of feel like it's dumbed down? And the answer is absolutely not. Because let's say you walk in this class, you got a PhD in chromatography, you've done this your whole life, and you're sitting in the back of my class, and I give you the shop mall analogy. You're going to walk away saying, you know what? That was a pretty good analogy. And the next time someone asks me to explain chromatography, I'm going to explain it that way. It also gets you to understand the parameters that you could change a little more. So if we do the shop mall analogy, we start talking about how fast is the moving sidewalk going? How does that affect the separation? So not only does the analogy help sort of establish how it works, but it helps us, further expand it. So believe it or not, I use the same analogies for the scientists, for the lawyers, for the high school dropouts. I don't see that it makes a difference at all.
Fair enough. Yeah, as I mentioned to you before we started recording, I'm at a marketing conference right now, and certainly every introduction I do, I'm explaining the type of work that my company's equipment's used in and explaining chromatography, mass spec to people who aren't familiar with it. So yeah, I would think that's the best strategy to use those examples that everyone can relate to.
Yeah. Think about my lawyer customers. They're going to have to explain this to a jury. 12 people have never heard of the word chromatography. And in their discussion, they're going to have to explain that. And they make very good use out of things like the shop mall analogy, as well as my scientist customers. I got one gig where I was asked to spend one day with the appellate court judges of the state of Texas. So it's me and a bunch of judges. And the topic was teach them GC. And I learned so much from them on how to teach because they would do things like, I talk about calibration. And they're like, wait a minute, you bought a GC, spent $75,000 on an instrument to measure, in that case, it was alcohol and blood. And you told me the GC doesn't know alcohol, doesn't know blood, doesn't know. So it's really funny. They're like, from an outsider, if I say to a scientist, calibrate your GC before you trust it, every scientist says, duh. But to a non scientist, calibration is a really foreign concept. So having really smart people who are not in the industry at all ask you questions, to me, made me a better teacher because I came up with more analogies. Like, how do I teach judges calibration? Came up with a really cool analogy using a butcher scale and that kind of stuff. So it actually helps me become a better teacher, even for my high-end customers.
If someone's watching this video and they hope to enhance their lab skills, what's one key takeaway about mass spec they should absolutely understand?
Yeah, that's a boy. That's a great question. I think that understanding the fundamentals. Don't be afraid to step in there instead of saying, "Oh, it's a magic box and it produces this picture." Understand what that picture is. It's smashing apart a molecule. Now you see the fragments. That's why the fragments are there. So I would not be afraid of the fundamentals. And then if you wanted like a really cool little tip into how to get a job doing mass spectrometry, understand the software. Because let's face it, all of us today are running the mass spec through the software. And if you have a good handle on how to run the software, you can do some amazing things. So a piece of hardware, and if you don't understand the software, you can't do anything with it. If you understand the software, you can do great things. So even out there for free, you can do tutorials. The big players out there, I mean, obviously, you're going to see folks like Cyax, Agilent, Waters, Shimatsu are going to be the big players out there, and they each have a data system that runs their mass spec. I would really take a look at that because once you get that, then you become a whiz kid in the lab.
One question I was very excited to ask you today was, what are some of the more interesting or unexpected applications of GCMS that you've encountered?
Yeah, boy, that's a good question. And I would say I get surprised. We do classes, I don't know, maybe 12 or 15 times a year, these 1 week classes, and every single time I teach a class, I find myself saying, "Wow, well, I never thought of that. What an interesting application." I had a class last week, had a young lady from Iceland, and she works at a company that makes pharmaceuticals, so drugs for the eye. And I don't know, I was just sort of like, "Gee, who'd have thought there are eye drop companies in Iceland?" And we had someone from Jamaica, and they were the Jamaican Bureau of Standards. So we have NIST, the National Institute of Technology. It used to be National Bureau of Standards. Well, there's a Jamaican Bureau of Standards, and why wouldn't there be? I find it's interesting that chromatography is applied to things that you wouldn't even think of. We had the Metropolitan Museum of Art from New York. And I'm like, "What are you doing here?" They said, "Well, we do art restoration. You got this 300-year-old painting and it's all dirty and we want to clean it, but we have to know what's the film on it, what's the dirt made out of, and what's the paint made out of, because we don't want to erase the paint when you're erasing the dirt." So that fascinated me. Of course, the DEA is always fascinating because they tell great stories. There's stuff out there that, man, there's a lot of crazy people in the drug world that don't do drugs. If you learn nothing else, you see these chromatograms of stuff that people are selling, and there's some nasty things in there. Obviously, there's fentanyl and a lot of stuff nowadays, and there's a methamphetamine. Meth is in almost everything. How would I know that unless I hang out with DEA guys and we do analyses with them, and like look at street drugs? Like, oh my gosh, this is sold as, I don't know, pink cocaine is this Tusi drug, and it's actually just ketamine and methamphetamine mixed together. It's like, what? So I always find that fascinating because they always have new stories. I spent a couple of years in the late 80s, mid to late 80s, a couple of years of my life designing bomb detectors, working with explosives. And that's fascinating because we want to find the explosive before it goes off. So how do you find explosive? You smell for it, you sniff for it. So a mass spectrometer is amazing at telling it, hey, this mass is indicative of an explosive. So if you see this mass floating around, you turn on a red light, you send off an alarm. So that is obviously, you can imagine the importance of doing that kind of stuff. And you know, chemical warfare agents detected at extremely low levels of mass spectrometry. But then I work on some fun projects. We did whiskey, and whiskey is fascinating. There's one big compound, it's ethanol, but then there's a bunch of other things. So if you look at vodka, it's just one peak, ethanol, nothing else. If you look at whiskey, you get a bunch of the what they call impurities. I'm not a whiskey fan, but there's like isoamyl alcohol, and so it's neat to look at two different whiskeys, and you could tell sort of a high end versus low end. Some of these impurities are lower levels, things that have aged longer. So that to me is sort of one of those, wow, never thought that we'd see a chemical difference. Started off as a very boring method request, and that was to look at edible oils. The mafia makes a lot of their money today by adulterating olive oil. They take olive oil, they mix it with cheaper oils. Who's going to know if there's corn oil in there? Well, we'll know because we can analyze it. So we did that, and it was involved. There was a lawsuit involved, and it was an $80 million lawsuit, and it all had to do with vegetable oils and messing with vegetable oils. We've done work for the natural vanilla industry. because natural vanilla is a really hard product to make. I mean, vanilla plant, they have to be they have to be pollinated by hand, every single plant. So it's very, very expensive to make real vanilla extract, but it's really cheap to make fake vanilla extract. And chemically, we can tell the difference. So that's, to me, is the fun thing about chromatography and mass spectrometry is you don't have to rely on someone to trust them to say this is what something is. You can say, hey, you know what? Let's go in the lab. Let's find out what that something is. So those to me are the ones that come to mind, and I'm sure for each one of those, there's another dozen fun ones that I just haven't thought of.
Absolutely. And that's very relatable for me in my work in terms of trying to visit several dozen customers each year who are using our nitrogen evaporators. And sometimes if I'm visiting a lab that's doing mostly EPA related work, I know what they're doing.
Right.
And because I know the regulated methods, where academic research, it could be any type of lab, whether it's food safety or people who are deriving their work from a EPA method. But then there's certainly a lot of interesting labs, like one I was able to visit, Alchemist Labs in California, where they are basically verifying a lot of the active ingredients in a lot of the over the counter medications that are sold at gas stations, a lot
Oh
of
my.
those energy related, where it's a really hard to regulate industry because people just can make these claims. The FDA saying, we haven't verified these claims, but they are able to test these products to see, oh, is there actually this much guarana extract for energy? Or it's really amazing work.
Yes, that's a good. If you learn nothing else from that, don't buy your drugs at a gas station because there's very little regulation on what's in that stuff and what's. So that's interesting. So my guess is you learn a lot from your customers in the nitrogen evaporator business because you're visiting them and they're showing you applications that maybe you guys hadn't even thought of. That's really cool.
Totally. And that was one of the first customers I had visited who was doing thin layer chromatography, where that wasn't something I was super familiar with, because I would say I would connect 80% of our business to LCMS or GCMS. So learning more about something like thin layer chromatography was definitely interesting. And now we're starting to see more interest in GCGC, which is another one of those topics that I wasn't super familiar with until I started visiting more people.
Yeah, multidimensional GC is a hot topic. I always say that all the fanboys are doing that these days. I hang out at conferences, the ACS national meetings, and Pittsburgh conference, and you see a lot of people talking about multidimensional GC or GC by GC. So it's a fascinating topic, and you're going to see more of them out there because it's becoming mainstream.
Now, I know this is a big, giant question, but I'd love to hear whatever thoughts you'd like to share. How do you see mass spec technology evolving? And is there any way for chemists today to start preparing for some of the changes we see coming in the next few years?
Boy, that's a yeah. I'll put on my prediction hat and say that if I look at chromatography, mass spectrometry, the big question I have is what's AI going to bring to the table? Because I could think of some very obvious things. Like, I teach people all day long how to look at peaks. You look for tall, skinny, symmetrical peaks. You don't want shoulders. You don't want tails. Well, a computer can do that and maybe tell me when I have a problem before I know I have a problem. So I think the AI, we all already see some pretty heavy computer stuff in the mass spec part of the world. So I think it'll be interesting to see what AI brings. In terms of technology, you're always going to see everyone wants lower sensitivity, everyone wants lower and lower detection limits. So I think you're going to see. I always joke that the Moore's law's version, Moore's law is in the computer world. In our world, every generation of mass spec is 10 times more sensitive than the previous generation. That's not exactly true, but we see a huge gain every generation of instrumentation. And most of the gains, from what I can tell, are really cool electronic stuff, like figuring out a way. I always describe a mass spec as we're creating a beam of ions. So it's like a flashlight. And this beam, I'm shooting across the mass spec. I'm doing something with it, but it's a beam of ions. And the beam is going to start to spread out, start to diverge. And I'm going to lose sensitivity because I'm not going to have as many ions making it to the detector. So a lot of what we see in the newer mass specs is what I'll call collimating lenses that are electronic magnetic that are refocusing the beam. The tighter the beam, the more ions we get to the detector. So there, I think electronics are going to continue to get better. So we're going to see sensitivity get better. I always question, um, what is do we need more sensitivity? And that's not the right way to put it. But what I find is that in a lot of regulatory environments, whether you're doing environmental stuff or you're doing pesticides in food, pesticides in cannabis, it seems that like the regulators just take the easy way out and they choose the regulatory limit to be the lowest detection limit of any instrument. So in other words, if someone comes out with an instrument that's 10 times more sensitive, all of a sudden that becomes the new law. And I sort of, that to me says, well, they're not setting the law for real reasons. They're setting it for just based on what the instrumentation is. So it is sort of a little dangerous part of what we do is we're going to make them more and more sensitive. The question on the other end is this value, does it mean anything? If I can find one part per quadrillion of uranium in someone's blood, does that mean they're radioactive? And the answer is no. So that's the challenge as we get to more and more sensitive instruments. And then I also take another big step back and I say, I interact with a lot of people in big companies, big industries, and I see a lot of people in the industry are doing things the way they did in 1988. It seemed like everyone sort of came to this level of technology and stopped adapting new stuff. So just learning the fundamentals, just learning things like pulsed injections, been out there for 20 years and no one is using it, no one knows about it. So to me, just get a feel for what's already out there, understand what's there and how it works. And even little improvements are big for industry because, like I said, it's amazing how many times you'll tell them something that came out 20 years ago and they'll run out and be like, oh my gosh, this has changed our lives. So understanding the fundamentals of GC, mass spec, and LC, I think it'll take you a long way into seeing what's going to happen next.
It can certainly be a pain to update workflows and operating procedures, but there are certain improvements and efficiencies to be gained by trying to push that change forward. Absolutely.
Yeah. I'm always interested in faster analysis. I'm always frustrated that chromatography still takes 20 or 30 minutes. It could be done in 2 minutes. It could be done in 2 seconds. So I'd like to see more. I think we'll see more of that grow out there because we have the capability to do it. It's just that people aren't doing it.
Absolutely. Well, Lee, this has been great. I really appreciate you sharing with the audience. I know I'll get a lot of great feedback on this episode because, frankly, in terms of all the presenters I've ever seen, you've done the best job at explaining these concepts
Yeah.
easy to understand way. And I've learned a lot from you, and I really
Oh,
appreciate the work you're doing.
oh. I've been practicing for 30 years, so I'm getting better.
Absolutely. Thanks so much, Lee.
Yeah, excellent.